Welcome back to The Explainer. Today, we're diving deep into a microscopic battlefield that's happening inside all of us. We're going to look at the incredibly clever and sometimes terrifying strategies of gastrointestinal bacterial pathogens.
So let's start with a number that is, well, it's pretty much impossible to wrap your head around. 5 nonillion. That's a 5 with 30 zeros after it. To put that in perspective, that's more bacteria on Earth than there are stars in the observable universe. They are everywhere. They're a fundamental part of our world.
And that leads to a really important question, right? If we're swimming in this sea of microbes, why are we constantly sick? Well, the answer lies in this invisible, non-stop war. It's an evolutionary arms race between our body's amazing defenses and a few highly specialized microbes that are armed for battle. So to understand how we stay healthy, we've got to meet the invaders.
Now, most bacteria we run into are totally harmless. Some are even super helpful. But a select few are classified as pathogens. And to really get what's happening in an infection, we need to speak the language of the fight.
So what exactly is a pathogen? It's not just any old microbe. It has to do two key things. First, it has to successfully set up camp in a host. It has to colonize. And second, it has to cause damage. And that damage can happen directly from the bacteria itself. Or, and this is really interesting, it can happen indirectly, by tricking our own immune system into causing all the damage.
Okay, this slide highlights a really critical distinction between two words we hear a lot: pathogenicity and virulence. Think of it like this. Pathogenicity is just the ability to cause disease. It's a simple yes or no. A common cold virus? Yes, it's pathogenic. But virulence is the degree of harm it causes. That cold virus has pretty low virulence. Something like the Ebola virus, on the other hand, has incredibly high virulence. It's the difference between a skirmish and an all-out war.
So how do these pathogens fight? They use this specialized arsenal called virulence factors. Honestly, you should think of these as their tactical gear. Adhesins are like molecular grappling hooks to hang on. Evasions are like stealth cloaks to dodge our immune system. Invasins are the tools they use to breach our cells. And toxins? Those are their chemical weapons. Understanding these is so important because it helps scientists develop therapies that can disarm the bacteria instead of just trying to kill them with antibiotics.
And how do scientists actually prove, without a doubt, that a specific microbe causes a specific disease? They use this classic set of rules called Koch's postulates. It's basically the original detective's handbook for microbiology. There's even a famous case where a scientist actually drank a culture of Helicobacter pylori himself just to prove it caused gastritis. He fulfilled that third postulate, got sick, and later won a Nobel Prize for it.
So here's the crucial point. An infection doesn't just happen instantly. It's not a single event. It's a carefully executed, multi-stage process, and it all hinges on one critical first step.
This slide lays out the typical invasion plan, this 5-step cycle. A pathogen has to attach, it has to evade our defenses, it has to multiply, then it causes damage, and finally, it has to find a way to get to a new host so we can keep going. It's a whole campaign, and it all starts with attachment.
Before a pathogen can do any real harm, it has to stick around. It can't just get washed away by the body's natural processes. So it uses these molecular grappling hooks called adhesins, which are often on these little appendages called fimbriae or pili, and they latch onto very specific receptors on our cells. The bottom line is, no stick, no sick.
Okay, so once they're attached, the invaders come face to face with our body's incredible security forces. But these pathogens, they've evolved this amazing array of tactics to slip right past our guards and breach the fortress.
You know, our bodies have these great frontline defenses, like a thick mucus barrier or patrolling immune cells called phagocytes that are designed to just eat invaders. But for every defense, pathogens have a countermove. They can release mucinase to literally dissolve the mucus. They have IgA protease to chop up our antibodies. They even send out these things called cytophores to steal the iron our bodies locked away, because they need it to grow. And some even wrap themselves in this polysaccharide capsule, which is basically an invisibility cloak to hide from those phagocytes.
Evasion is all about survival. But the real damage, the symptoms that we actually feel when we're sick, that's often caused by a pathogen's ultimate weapons, its toxins. So bacteria basically deploy two main kinds of toxins. You've got endotoxins, like the lipopolysaccharide or LPS, that's built right into the outer wall of gram-negative bacteria. Think of it like a booby trap. It's only released when the bacteria dies, and it triggers this massive inflammatory response that can cause fever and shock. Then you have exotoxins. These are totally different. They're proteins that are actively launched by living bacteria, kind of like guided missiles with very specific targets in our cells.
And many of these really potent exotoxins have this brilliant two-part design. It's called an A/B subunit toxin. The B subunit stands for binding. It's like the key that finds the lock on our cells and opens the door. And that allows the A subunit, the active part, to get inside. That's the warhead that actually carries out the mission and causes all the damage.
Okay, so we've covered the theory of battle, right? The strategies, the weapons. Now let's go to the front lines and look at the actual battle plans of some of the most notorious GI pathogens out there.
First up, virotoxin-producing E. coli, or VTEC. Its weapon of choice is the Shiga toxin, and this thing is nasty. It's an AB toxin that gets into our intestinal cells and acts like a saboteur. It finds our ribosomes, the cell's protein factories, and just shuts them down completely. This kills the cells, which leads to bloody diarrhea and in really bad cases can cause life-threatening kidney failure called hemolytic uremic syndrome.
Now, contrast that with a different strain, enterotoxigenic E. coli, or ETEC. This is the main bug behind travelers' diarrhea. It doesn't kill the cell, it hijacks it. Its toxins, LT and ST, mess with the cell's internal communication system by jacking up the levels of signaling molecules called cyclic AMP and cyclic GMP. This basically tricks the intestinal cells into opening the floodgates and pumping out massive amounts of water and electrolytes. And that's what leads to that severe watery diarrhea. Then you've got Campylobacter jejuni, which has a completely different playbook. Its main weapon is the cytolethal distending toxin, or CDT. This toxin travels all the way into our cell's nucleus and acts like a pair of molecular scissors, literally causing double-strand breaks in our DNA. That damage triggers something called cell cycle arrest, which stops our cells from dividing and leads to a huge inflammatory response.
This table does a great job of summing up these unique battle plans. You can see that direct line from the virulence factor to the disease. For VTEC, the virulence factor leads straight to cell death. With ETEC, it's the toxins causing that crazy ionic imbalance. Campylobacter CDT toxin stops our cells from dividing, and maybe the most incredible one on here is Helicobacter pylori. It uses an enzyme called urease to create this little neutral pH shield around itself, which lets it survive in pure stomach acid. I mean, that is just an unbelievable feat of adaptation.
So, what's the big takeaway here? At the end of the day, every single infection is just another battle in a much larger, ongoing evolutionary arms race. Pathogens are constantly evolving new virulence factors to get an edge, and our immune systems are constantly adapting with new defenses to fight back. It is a dynamic, relentless, and frankly, amazing cycle.
And that leaves us with a final and pretty crucial question. In this endless war, especially as microbes adapt to our modern medicines and develop antibiotic resistance, what new strategies will they come up with? What will the next generation of virulence factors even look like? And how are we going to have to adapt our own strategies to keep fighting back?